Welcome to the thermochemistry unit. Here we're going to be talking about chemicals and their heat energy, thermochem. There are two kinds of heat energy within chemicals. One being that they are still water and now it's warmer water, it's moving faster, colder water, it's moving slower, still water. So that would be a kinetic energy change because it's just about the movement of the molecules. That's what we're going to be talking about, or the vibration of the molecules. That's what we're going to be talking about today is heat energy. The other type is reaction energy, a potential energy, bonds breaking, bonds forming, and the exothermic or endothermic energy released or energy absorbed in that reaction. That is for another outcome. So, and of course, we're going to put those energies together because potential energy can be converted into kinetic energy, right? So, the first thing we're talking about today is the kinetic energy. Kinetic energy is represented by this formula here, Q, which is often called heat energy, but also because we have one equaling the other, the potential energy equaling the kinetic energy, sometimes this wording is a little bit ambiguous, right? How much energy was released by the reaction into the thing it's warming up, right? So imagine you have a campfire and you're warming your hands up. The energy released by the campfire is going into your hands. And so the amount of energy entering your hands, the amount of energy lost by the campfire is the same thing as your Q equals MC delta T for your hands. So this part here is ambiguous in its naming, so don't rely on that. But if you understand that this is a kinetic energy, then that is every time the same. Kinetic energy is your Q. So of course, energy is measured in joules. M is your mass, which is measured in grams. For chemistry, I understand that when we're talking about energy in physics, it's kilograms. Here it's grams if it's joules. Specific heat capacity is joules per gram degree Celsius, and delta T is temperature change. So Q equals MC delta T. We know that by grade 12, you can plug in numbers and get an answer. That's not going to be the hard part. You are going to have to memorize this formula. It's not on your data booklet, but it also, you could use your units to help you answer it and just use unit analysis. That's how we create formulas as scientists. Okay, so the thing that's going to make this tricky are my units. If I have grams, it ends up being joules. But if I have kilograms, I'm going to get kilojoules. You the kilo is what I'm going to say frequently in this unit. Equally, I could have kilojoules over kilograms because in this fraction, kilojoules divided by kilograms degrees Celsius, you should be able to see how the kilos cancel each other out. And so canceling each other out means that I can do whatever I want. I could put giga over giga, right? It doesn't really matter what I have. And then my answer would be gigajoules. So the hard part about this is going to be units. Maybe the hard part is algebra. And obviously you have to know that this is about kinetic energy. That part's really important. I'm not changing the water or the air. I am not reacting the water or the air. Instead, I am just making it vibrate faster or vibrate slower. So let's try a couple examples. Here, this one is quite straightforward. Find the heat energy. So it's looking for Q here, required to change this mass of air from 10 degrees Celsius to 20, well, that should say 22 degrees Celsius. Okay, so if you are looking in your data booklet on page 3, and please don't just Google the specific heat capacity, actually use your data booklet so you become familiar and comfortable with where to find these. So the specific heat capacity of air, the C of air, is equal to 1.01 joules per gram degrees Celsius. And this temperature change here, going from 10 to 22, is 12.0 degrees Celsius, 12 being, 0.0, pardon me, being the last decimal place is subtraction. So I look at my decimal places for significant digits. So 12.0 for significant digits. So Q is equal to MC delta T. The M here is 2.50 kilograms. The specific capacity is 1.01 joules per gram degrees Celsius, and that temperature change is 12.0 degrees Celsius. Now, I did say that we want to pay attention to our units, right? So if I have the degrees Celsiuses canceling out, the grams canceling out, then I'm going to end up with kilojoules. The shortcut to that is if you have kilograms, you're going to get kilojoules for your Q, you the kilo. Okay, so multiplying that all in my calculator, I get 30.3 kilojoules for my answer. Okay, so pretty straightforward question, other than the units, maybe. Here's something that requires a little bit more algebra. A 250 ml glass at that temperature was placed in a fridge for some time. If the water lost that many kilojoules of energy, what is the temperature of the water after 25 minutes? So dissecting the information here, I see here that I have initial temperature. Here I have a volume of water. 25 minutes does not apply to my Q equals MC delta T, so it's just extra information for me. If the water lost that much energy, so we're talking about Q here because all it did is get colder, so this is about kinetic energy, and therefore I don't need to worry about anything other than Q equals MC delta T. What is the temperature after? So it's looking for final temperature. Now, in order to have Q equals MC delta T, we have to recognize that my volume is actually my M. Now, there's different ways of teaching this. Some textbooks will have another formula that's VC delta T. I just think that's a waste. So for here, I want you to understand that my M is the volume because, and you have to know this, 1 gram is equal to 1 milliliter if it's water or a solution. Okay, so if I had some salt solution, if I had some copper sulfate solution, if I had some HCl acid solution, all those aqueous solutions are going to also be 1 gram is 1 mil. So this says 250 mils, so then that is actually 250 grams. My specific heat capacity, this is of water, so I look that up in my data booklet, and it's 4.19 joules per gram degrees Celsius. And the temperature change is what I want to find out, because if I can find my temperature change, then I can find my final temperature. And that Q is 2.320 degrees kilojoules, pardon me. We treat Q as an absolute value. Whenever it's asked, it's always about absorbed, lost, gained. It's asked for it in an absolute value. So we treat Q as an absolute value. It's not going to have a negative or a positive in front of it. Everything here is about its absolute value. So solving for delta T here, right? I'm going to divide both sides by 250, divide both sides by 4.19. And my delta T ends up being 2.21 degrees Celsius. Okay. So if my delta T is 2.21 degrees Celsius, then I look at the situation and I'm like, oh my goodness, it's being put in the fridge. It's getting colder. So in order to find my TF, and this is much easier than doing the algebra of TF in here. In order to find my TF, I'm going to go, well, it started at 21 or 20.3 degrees Celsius. It got colder, so I'm going to subtract 2.21 degrees Celsius. And so my final temperature is then 18.1 degrees Celsius. This final temperature should have 1 decimal place because it has 1 decimal place, 2 decimal places. So when I'm subtracting, my final answer has 1 decimal place. Also, your delta T is not always final minus initial. It is your maximum temperature change. So if I were to do a reaction, eventually that reaction will finish and go back to room temperature. And so it's not your final temperature, but rather it is your maximum temperature change. That's what delta T is. So that with that theory in mind, that's why I'm not doing TF minus TI for my delta T. I'm doing it in 2 steps. Okay, so I hope you understand what Q equals MC delta T is, how to use my formulas within this, the understanding of what specific heat capacity is, and understanding that Q is about kinetic energy.